Okay, so let's begin. This is lecture 16 of the course on galaxies. So in the last class, we looked at how stellar population synthesis could be used to uh, predict the star formation history of a galaxy, which was the main parameter we wanted to get at. Once you know the star formation history of a galaxy, which means at what time it formed, how many stars, that is the function psi of t, you can integrate that function and get the total stellar mass of the galaxy. Of course, not all stars will remain as stars. Some of them will go supernova or become red giants and turn into white dwarfs, etc. So when you do that, you have to add in the mass of the remnants as well. So you integrate this quantity, and then the integral will correspond to the stellar mass that's in the form of stars, plus the mass of the remnants. You can also use that to, because you know the energy balance of the galaxy now, how much starlight is emitted. And if you know how much dust has been created, you know how much the dust will absorb and re-radiate in the far infrared. So you can use the properties of the dust to predict the far infrared properties in terms of emission from the dust, and also the optical and UV properties in terms of absorption of radiation by the dust. So that gives you the properties of the dust. And perhaps most importantly, you can measure the instantaneous star formation rate. Okay, so how many stars have formed recently, the psi of t, if integrated over, let's say, the last 100 million years or so, will give you an average number of stars being formed at the current time. So all of these parameters are important, and they basically tell you the life story of the galaxies. Star formation is the most important parameter that you measure in order to measure how the galaxy has evolved over time. This, of course, is like I said yesterday, is a time-consuming process, because what you typically do is that for the entire parameter space, your entire parameterized star formation history, different IMFs, and different dust properties, etc., you construct a modeled spectrum, and you compare that modeled spectrum or spectral energy distribution with your observed SED, right? And you try to minimize the difference between your model and the observed distribution, and then the model parameters of that model are your best fit parameters. This takes a lot of time, because the number of models that are typically constructed are in the millions, and there is no easy way to determine if one model fits well, which other model will fit equally well. So what is usually done is a sort of brute force method. So if I have 10 million models, I will compare each model with my data, and I will compute a chi-square, and then I will then decide that, okay, this is my model with the least chi-square, and therefore that is my best fit model. This is very time consuming. Typically, it takes of the order of a minute or so to compare 10 million models with say 10-15 data points, which are your broadband spectral energy distribution measurements. So if you have tens of thousands of galaxies in your sample, that becomes very slow process. So in recent times, people have tried to look at whether stellar population synthesis can be simplified via some kind of artificial intelligence based process. So there is something called deep learning. So this diagram represents, so on the left side, these circles represents your input parameters, which may be your data, your flux measurement in optical, infrared bands, etc. And there is a artificial neural network with many layers. That's why it's called deep learning. And the weights of each of these layers get set by during the training process, where you give it an input and say that, okay, for this galaxy with these fluxes in the various bands, the star formation rate is so and so, the stellar mass is so and so, the dust luminosity is so and so, etc. So you give it the parameters that you want to measure, get out of the network, and you do that for thousands of galaxies in the training process. That takes some time, maybe an hour or so. But once trained, the network weights are fixed. So you can give it any input you want, and it will instantly spit out an output. So it's very, very fast. Once trained, it's incredibly fast. It's able to obtain outputs for 20,000 galaxies in less than 1 second. So instead of doing one galaxy a minute, you are doing more than 20,000 a second. Okay, so enormous improvement, 5 or 6 orders of improvement in speed. But this doesn't have any knowledge of the physics. Whereas your stellar population synthesis models are based on the physics of stars, right? In physics of the dust. This is just completely blind. Here the input parameters would be your fluxes or your spectrum. So if you have measured the spectrum at, let's say, 1,000 points, you can give 1,000 input parameters here, no problem. And the output parameters are whatever you want to get out eventually, just the final product, the current star formation rate, or the stellar mass, or something. Obviously, it's a function. Some complicated nonlinear function of the input parameters is your output parameter. Okay, but in stellar population synthesis, you try to determine that function using the laws of physics. Here you say that, okay, we don't care, whatever be the laws of physics, this is the input, this gives empirically, this gives me the output. Okay, but remember, in order to do that, you have to give the outputs during the training. And when you give it the outputs during the training, this deep learning network learns to imitate the behavior of the stellar population synthesis model. Okay, it cannot do better than that. So if you have some fundamental flaw in your stellar population synthesis model, okay, let us say your isochrones are all wrong, correct? Then this thing will learn all the wrong things and give you wrong outputs. So it will just try to give you the similar outputs to that. But the high speed is still useful, given the size of upcoming galaxy surveys. So in Rubin LSST, for example, we will detect 20 billion galaxies, right? If you want to do it one by one, stellar population synthesis on all of them, it will take forever. At one galaxy a minute, okay, it will take 20 billion minutes to do this. So we don't want to do that. One could also use a hybrid approach. So use the deep learning to narrow down the parameter space and then fit SPS models only around that parameter space. So you use deep learning to say that, okay, the deep learning tells you the star formation rate is, let's say, 2 solar masses per year. Okay, so deep learning is not going to be way off. The true star formation rate is unlikely to be 200 solar masses per year. So what you do is you then pick models which have star formation rates between, say, 1 and 3 solar masses per year. And you do that for all the other parameters. And so instead of then comparing with 20 million models, you may compare with, say, 2,000 models, which is very fast. So in this hybrid approach, you have the advantage of the physics in terms of the correctness or the believability of your results, but you also have the advantage of the deep learning method to narrow down your parameter space. So, yeah. Yes, yes. But you don't know the star formation rate. Now, everything is a little bit model dependent. So the star formation rate, if you want to measure the instantaneous star formation rate, Okay, you have to observe how many stars it is forming over the next 10 years. We don't have time to do that, right? So what we do is we have some model. So even star formation rates that are determined by some other calibration. For example, there are, if you know the far infrared luminosity of a galaxy, there is a linear calibration that maps onto the star formation rate. So if you measure the far infrared luminosity, use that to get a star formation rate. But even that is dependent on model. So you could do this if, and people have done that, which is like you don't use observations at all. What you use are numerical simulations, wherein you know everything because you have put it in by hand, or it can be measured with zero noise. So if in the numerical simulation you know that okay, this galaxy has a star formation rate of so and so, then you can train using that. But that also is a little bit model dependent, in the sense that when they have a numerical simulation, but when they convert from the measured physical parameter space to the observable parameter space, they use a mapping function which is model dependent. So when they say that, okay, as per our simulation, the far infrared flux that you measure should be so and so, right? That mapping is model dependent. So even that process of training on simulation is not completely bereft of the model. So it's not very easy, right? For other things, it's easier. So for example, if you're trying to use a deep learning network to classify separate stars and galaxies, so that humans are very good at. They can create very good training samples, which are 100% stars and 100% galaxies. And they can use that as training input to the neural network. And then it performs brilliantly well. So then there is no problem. Because there is a unambiguous truth value. Whereas here in stellar population synthesis, the outputs are not unambiguously true. Even from the SPS model, they have uncertainties. They even have what are called catastrophic failures, which means the galaxy actually has a star formation rate of 200 solar masses per year, but your SPS is predicting only 2 solar masses per year because it got some correlated parameter like the dust luminosity also completely wrong. So that also happens. So, okay, so how well does this deep learning method work? So what is shown here is on the x-axis is the stellar mass that you get from one of the stellar population synthesis codes called MACFIS. And on the y-axis, you have the stellar mass as predicted by deep learning. And this is your y equal to x line, okay? And very close to it is a dashed line, which is the best fit line to the data. And this is a sort of zoomed in version of that, where you're just plotting the deviations. And you can see that the deviations are mostly random, with very little systematics. And all the way from 10 raised to 9 to 10 raised to 11.5 solar masses, 2.5 orders of magnitude, you have pretty good fits with small scatter. Yes, it does depend on what kind of deep learning algorithm you're using and so on. Yes, definitely. You can predict the SFR also reasonably well. So here's the same plot now for the star formation rate. And again, over a wide range from 10 raised to -2 solar masses per year to about nearly 10 raised to 2 solar masses per year. These are what typical ellipticals, or ellipticals would be even below this. These are like heavily star forming galaxies. Huh. It does, but it also has a trade-off, because beyond a point, it doesn't do anything. It doesn't improve things. and it slows down the training. So because there are more layers, there are more weights to be determined, you have to spend more time in the training. So there is a trade-off. So like, for example, I think in this work, we had about 14 hidden layers in between. The dust luminosity also can be predicted. So what we did in this work was to try and predict 3 different properties: the star formation rate, the integral of the star formation rate over the lifetime of the galaxy, which is the stellar mass, and we tried to predict the dust luminosity. These are 3 broad properties of galaxies, which we need to know to understand galaxy evolution. Okay. Yeah. Now we change gears once again and begin to talk about galaxy formation and evolution. Yeah. Yes, so those will either leave a remnant. Okay, supernovae, sometimes very massive stars leave no remnants. So those will leave no remnant, but most of the stars will leave a remnant. Okay. Some are dying, but the star formation rate is the formation rate only. It's like a birth rate. You don't subtract the death rate of stars from that. Yeah. Okay. So this is a brief history of the universe. I'm sure you've encountered this kind of figure in other courses. So you had the Big Bang. There was an inflationary phase in the fraction of a second after the Big Bang. And then the universe continued to expand. And then at about 400,000 years after the Big Bang, you had the temperature had cooled enough for the plasma to get converted into atoms. So you had electrons and protons coming together to form hydrogen atoms. And then you had what are called the dark ages. And during the dark ages, nothing much happened visibly. But of course, the hydrogen was collecting together under its own gravity, and the gravity of the dark matter halos, in which were also forming at that time. And eventually, a stage was reached where densities, pressures, temperatures, etc., were suitable for nuclear fusion to start, and the first stars were formed. Okay, and we don't know exactly when the first stars formed, but the rough number is like this: about 400 million years after the Big Bang. And then, of course, the story of galaxies began from that point, because the stars then went on to build galaxies. The galaxies continued to evolve over time. They continued to form stars. They had a lot of merger events. They had active galaxies being formed within them, and so on, until eventually we reach the local universe. So far we have been looking mostly at this end of the funnel, right? We are looking. We've been studying the structure, kinematics of galaxies in the local universe. Now, here onwards, we are going to go a little bit into the high redshift universe and look at high redshift galaxies, how they are discovered, what their properties are, and so on. And what we are going to leave out is a very, very important component, which is going to come in your course in the next semester, in your course on the interstellar and the intergalactic medium. Because much of what we know about the high redshift universe is informed by studies of absorption line systems along the line of sight to distant quasars. Okay, so we know either through radar observations or optical observations, we know a lot about the hydrogen clouds in the intervening space, those that don't glow very, very strongly in the optical bands. but we also know quite a bit about the high redshift galaxies. Interestingly, we know more galaxies between redshifts 3 and 5 than we know between redshift 1 and 3. Okay, and we will come to that a little bit later. But before I go there, I'm going to show you a simulation, which is from a simulation called Illustris. So let me pause for a second. So what this simulation does is that there's a very large box in which the simulation is carried out. It's a full simulation, meaning it's not only a dark matter particle simulation. It's also baryonic simulation within the dark matter halos. So it first simulates the formation of the dark matter halos, and after that it simulates the formation of galaxies within the dark matter halos. And it takes into account all kinds of things like the metallicity evolution of the galaxies. It takes into account how many stars will form and how much feedback there will be. It also takes into account how many AGNs will form at different points in time and how much will be the AGN feedback and so on. So it allows you to trace almost everything: the metallicity evolution of the universe, the star formation rate of the universe, the AGN number density of the universe as a function of time, and so on. So this particular video was made from this very large simulation, and this was done in the second half of 2013. And it ran for many months on a very large supercomputer. And so it's one of the largest simulations. Simulations like these take many years to plan because you are consuming so much resources on an expensive supercomputer. You have to write your codes, you have to test your codes, you have to plan your schedule, your run, etc. But they did all that. So this is a very big team of people who have carried out this simulation across many countries. But this is one of the best simulations that has been done so far. There are many smaller simulations that have been done by various people. This is one of the larger ones. So here, what you see here is the time since the Big Bang on the x-axis, and the thing advances by 100 million years. I should change the brightness. The thing advances by 100 million years every second. So let's play the simulation. So we are rotating, the camera is rotating around your simulation box so that you can see it from all angles. So initially in the first billion years or so, what is essentially happening is the cosmic web is forming, and already you can see that there are structures. I mean, there are regions where you don't have too much baryonic matter. Those are your voids. Then there are filaments like these. Okay, some of the filaments are two-dimensional, so we call them sheets. And then there are knots. There are where the filaments, two or more filaments meet. There you have overdensity. And these are the places, the locations in the universe where eventually clusters are going to form. So as time goes on, the stars begin to form in larger numbers. We are now well past the first stars stage, but still we are not forming stars terribly vigorously. What you will see as time goes on is an increase in the magenta color in the simulation box. So the blue corresponds to stars, the regions where stars are forming. The green corresponds to regions where the gas is there. So more green means higher density, higher column density gas. And what you will see as time goes on is that this green colored gas changes color and becomes magenta in color. And that magenta color represents high metallicity gas. So that represents, so this is low metallicity gas, green one. Magenta represents high metallicity gas. Now we are about 3 billion years after the Big Bang, and the star formation rate is stepping up. Simultaneously with the stepping up of the star formation rate, there is AGN activity is stepping up. So what you see like explosions going off over there is actually feedback from active galactic nuclei. So active galactic nuclei are one of the most powerful means of transferring energy into the intergalactic medium. And therefore, those are the ones that are also pumping out gas into the interstellar medium, intergalactic medium. So you can see that the space of between the galaxies is now occupied not by green colored low metallicity gas, but by this magenta colored high metallicity gas. And at the same time, the structures are beginning to grow. This simulation does not have the resolution to show you the formation of the giant spiral galaxies, etc., but it can show you the formation of clusters. And so you can see now that there are galaxies which are merging and beginning to form the kind of galaxy structures that we see in the nearby universe. So eventually, we reach a stage where you see a galaxy cluster. So this is the Illustris collaboration. These are the people involved from various places. And so what we are going to do during the remaining 6.5 lectures that we have is to try and understand this whole process of galaxy formation and evolution from both from a large scale perspective, this is like a cosmological perspective, but also from the small scale perspective, which is how exactly do stars form, how does dust contribute to galaxy evolution, how does the dark matter influence the formation of stars, etc. Okay. The quality of the HUDF, of the Illustris simulation is illustrated by this plot, by this figure. So what you have on one side, you have real galaxies, and on the other side you have the simulation. And as you can see, you can barely make out the difference. Can you guess which side is, left side is real or right side is real? It's very hard to tell, right? So it turns out that the left side is real. Actually, there are some stars. They should have put some stars on this side with diffraction spikes and so on. That would have made it hard. But these are some foreground Milky Way stars. There is one star over here, for example. And that is from the real image obtained with the HST. And this is from Illustris. So the colors, the shapes, the sizes of galaxies, their relative brightness, everything is coming out really well in the simulations. More small points are there. You're right. So that's probably true. That may be related to the size of this box. Okay. The real universe is a much larger box size, whereas this, although it's a very large box size, it's not as large as the full universe, and that may be creating this loss of information, in the sense that there are more faint points over here than there are here. Okay. So now we'll talk a little bit about chemical evolution of galaxies. By chemical evolution, we mean the change in the metallicity content of galaxies as a function of time. We can make a simple model of metallicity evolution by saying that at the formation epoch of the stellar population of the galaxy, okay, at time t equal to 0, no metals were present. So it was all hydrogen or helium and nothing else. So Z of 0 is equal to 0. The galaxy did not contain any stars at the time of its birth. So all baryonic matter was in the form of gas. The third assumption we make is that the galaxy is a closed system out of which no matter can escape or be added later on by processes of accretion or merger. Okay. This obviously is an incorrect assumption because we know that there is accretion and merger happening, and there's also stuff flowing out of the galaxy due to AGN and supernovae. So this is a wrong assumption, but as we shall see later, this is still useful to do a calculation based on this closed box model. The timescales of stellar evolution processes that lead to metal enrichment of the galaxy are small compared to the evolutionary timescale of the galaxy. Okay? So metal enrichment happens relatively quickly relative to the whole lifetime of the galaxy. So therefore, Z of t is a useful number to calculate. Okay. So if you of the total mass of a newly formed stellar population, part of it is returned to the interstellar medium. Okay. And it's a closed box system, so it doesn't leave the galaxy altogether. So it doesn't go into the IGM, it's our assumption. But we are allowed to throw gas or anything else, return it into the interstellar medium of the galaxy itself. And this is done by via supernova explosions and stellar winds. Okay, if you have AGN, you can do the same things, except that AGNs are so powerful that they'll tend to throw things out of the galaxy completely. So for the moment, we ignore AGNs, and we define this fraction as R, so that the fraction alpha, 1 minus R of a newly formed stellar population, is the fraction that remains enclosed in stars. And then we define a parameter called Q, which is the ratio of the mass in metals, which is produced by a stellar population and then returned into the ISM to the initial total mass of the stellar population. Then we can define a quantity called the yield, Y, which is simply Q over alpha, which is defined as the ratio of the mass in metals that is produced by the stellar population, that's Q, and returned into the ISM, and the mass that stays enclosed in the stellar population, which is alpha. Q and alpha are quantities that are natural byproducts of your stellar population synthesis models. Okay, so you will get them from your SPS models. If psi of t is the star formation rate as a function of time, then the mass of all stars formed in the history of the galaxy is just simply the integration from t equal to 0 to your present time of the psi of t as a function of time. Okay, so that gives you your total mass in stars, S of t. The mass that remains enclosed in stars, we can write that as small s of t, and naturally that's going to be alpha times capital S of t. For a closed system, the sum of the gas mass and the stellar mass is a constant. Okay, so you may ask, what about dust? In most systems, the mass of the dust is very small compared to the mass of the gas and the stars. Okay, so for the moment we ignore dust. So we write down that the mass in gas and the mass in stars is constant. Okay, at any given time, it's the addition is the same, and that is your, let's say, your mass in baryons, again ignoring the mass in the dust. And you can differentiate that expression and write down dg over dt plus ds over dt is 0. The mass of the metals in the ISM is G times Z. Okay, it changes when stars are formed. Through this formation, the mass of the ISM and thus also that of its metals decreases. So metals are returned back into the formation of new stars. But reverse process also happens. Transport of metals from stars into the ISM by the process of stellar evolution, virtually instantaneously compared to galaxy evolution timescales. Okay, it's virtually instantaneously has the caveat that all this metal exchange is mainly happening via the more massive stars, right? Because those are the ones that can explode, give rise to the next generation, and then maybe if the next generation also massive, again return metals into the ISM and so on. Whereas a star, a low mass star, if it forms, let's say 10 billion years ago, even now it has nothing has happened to it. It's on the main sequence, right? It is not exchanging metals with the gaseous interstellar medium. It is whatever, no metals are getting formed, in fact, because just hydrogen to helium fusion is happening. Nothing else is happening. Okay, anyway. Together, the total mass of the metals in the ISM obeys the evolution equation, which is the rate of change of, this is the total mass in metals, which depends on the star formation rate, it depends on the return fraction, it depends on the metallicity, and it also depends on this yield. Sorry, not the yield, the factor Q. Okay, and this is like a conservation equation. Okay, but ds by dt is just psi. So this equation can also be rewritten by replacing psi, ds by dt, psi with ds by dt, and you can write it in this form. So you can write the rate of change of g times z as a function of ds, the total mass in stars, depends on q, is q minus alpha of z. You can divide this equation by alpha, and using the fact that S is alpha times capital S and the definition of the yield that we had earlier, you can write down this differential equation. Okay. Now, once you write down this differential equation for a closed box model, dg by ds, okay, is -1, and dz by ds is minus dz by dg. So because whatever metals are gained by the stars must be lost by the gas, right? So if you do that, then you can write this this kind of equation, which relates your yield to the quantities that you have on the left hand side. And then you can write z of t as minus y log of gt over the mass in baryons, which is equal to minus y log of a parameter called mu g, which is basically just this. Okay. The mass in gas divided by mass of the baryons. Is the fraction of baryons in the ISM. So the total mass in the gas divided by the total baryonic mass of the galaxy is the mass of baryons in the gaseous phase in the interstellar medium. We plug in the initial conditions at t equal to 0, mu g is 1, because all the mass fraction is contained in the gas, and metallicity is 0. Okay. From this relation, we can see that with decreasing gas content in the galaxy, the metallicity will increase. In our simple model, this increase depends only on the yield y. And because the yield can be calculated directly from population synthesis models, z of t is completely defined. So now all of this analysis that we presented is very simple, just rearrangement of terms and simple linear differential equations, is true provided the assumptions that we had initially are all true. If it is in fact a closed box system, then you can predict using population synthesis models how the z of t is the metallicity of the galaxy is going to evolve as a function of time. So one can ask the question, how does this simple closed box evolution model compare with observations? It turns out not very well, because we know already, we saw that one of the assumptions was very broken, where mass continuously changes through accretion and merging processes. In addition, the kinetic energy transferred to the ISM by supernova explosions causes an outflow of the ISM, particularly in low mass galaxies, where the gas is not strongly gravitationally bound, correct? So it lose gas. So nevertheless, this relation is still useful. Why is it useful? See, whatever the star formation rate, star formation history, etc., is all encapsulated there. But why is the closed box model prediction of the metallicity evolution still useful? Conserved, yes. Yes. Correct. So for example, if you have, you predicted a metallicity of X, let's say, and your observed metallicity is X by 2. What does that indicate? Yes, there is some loss of metals which will not come back. So some metals got thrown out of the galaxy. Now, on the other hand, if it is twice, so you expected in a closed box model to have a metallicity of X, but you actually have 2X in the observations. What does that show you? That shows that there is some metal enrichment. So there has been some event by which metal enriched gas has entered into your system. Right? Yeah. Yes. Yes. So it turns out, I mean, these are small factors. So if you have star formation, the amount of mass that gets converted into radiation, okay, is very small. So for example, you know what is the efficiency of hydrogen to helium fusion, okay? It's 0.7%. So less than 1% of the mass is lost in the fusion process, provided 100% of the hydrogen gets converted to helium, which also doesn't happen. So when the sun goes off the main sequence, it is not as if it is going to use up every last gram of hydrogen and convert it to helium. That's not going to happen. So the conversion efficiency is low, plus the fact that not all gas gets converted into energy, means that delta mc square, that delta m term is quite small. So you don't have to worry too much about it, because all of these things, remember, in astronomy, very often we do things, if we are, first we try to do things accurate to 1 order of magnitude, okay? Then we try to do things accurate to 10%. Very, very rarely we try to do things accurate to 1% or better. You try to do 1% or better when you are trying to make a measurement that is buried deep in the noise. So for example, you're trying to measure radial velocities of a star to find a planet that is going around it. Now those radial velocities are very, very small. Your error bars are large. So there you try to make a 1% or better measurement. In galaxy evolution, in most of the things we are doing, we try to get to 10%. So if I can predict metallicity to 10%, if I can predict star formation rate to 10%, if I can predict stellar mass to 10%, I'm happy. I don't, we are not yet in a position to go beyond that. So that is why this sort of 1% or sub 1% effects are ignored. Okay. So this is an example, okay, of where this kind of closed box model is useful. Our simple chemical evolution model predicts that about half of the F and G main sequence stars should have a metallicity less than a quarter of the solar value because they formed early and are long-lived, correct? This implies that but that's not true. So this implies that the chemical evolution of our galaxy must be substantially more complicated than described by our simple model. Because at least in the solar neighborhood, we find most of the stars are having, even the F and G type, meaning low mass stars like the sun, are having near solar metallicity. It's not very different. Okay. So now talking of accuracy and 10% and 1% measurements, precision cosmology, which we have right now, is something that is relatively recent, only about 20 years old. Between 1950 and 2000, cosmologists were preoccupied with measuring the primary cosmological parameters, H0, omega, and omega matter. And there was immense controversy. So let me give you an example of H0. The Hubble parameter was sought to be measured, and that was done by basically measuring using some kind of stars as standard candles to calibrate distances and use that to measure the expansion of the universe at this time. The value of H0 that was consistently obtained by one group was 50 kilometers per second per megaparsec. And the value obtained by another group, so one group was led by Sandage, another by Devoculars. The other group was consistently measuring H0 of 100 kilometers per second per megaparsec. The discrepancy was a factor of 2. And these guys were saying you are wrong, these guys saying you are wrong. So it was just going back and forth, back and forth. And they were saying, okay, we will measure more, bring more measurements to prove that we are right. And they were getting more measurements. And again, they were getting, these guys were getting 50, those guys were also getting more measurements and getting 100. So the modern value is about 70 kilometers per second per megaparsec, which is exactly in between these two values. So that era is now over, okay, because there were many systematics that they were incorrectly accounting for in that epoch. And now we have entered the era of precision cosmology. Now there is a tension, but the tension between the Planck measurement and the other measurements is at the 2 sigma level. Okay, it's there, but now we are quibbling about it's 1% off or 2% off. That 25 years ago we are fighting about factor of 2. We want to understand how the universe evolved from a very primitive initial state into what we are observing around us today. Okay, galaxies of different morphologies, the large-scale structure of their distribution. We observe lots of clusters, and we observe active galaxies. And we are seeking to study the formation of stars and of metals, and also of processes that reionize the intergalactic medium. So that's the sort of thing. But this part, as I said, I am not going to cover in great detail, the reionization of the intergalactic medium. So we know that the universe was initially neutral after the recombination era. Then it got ionized, which means the intergalactic medium didn't have too much of neutral hydrogen. Whatever hydrogen was there, it was in the form of ions. And that's process, we don't know whether it happened very quickly or it happened over a period of time. And what could be the contributors to this reionization? Energy feedback from stars, okay, or energy feedback from the AGN. The relative contributions of these two are still some subject of controversy, just like the exact epoch of the start of reionization and the end of reionization is also uncertain. There are two broad techniques that people are using in order to understand this, besides, of course, theoretical work and numerical simulations. Observationally, there are two strategies people use. One is you first do a census of the ionizing sources. You find out how many quasars there are in the high redshift universe. You find out how much star formation is happening in the high redshift universe. And then you use that and some simple energy balance kind of ideas to find out how much of the universe would have been ionized by these sources. That is one. The other approach, which is followed by radio astronomers, is to say that, okay, we will not map the ionized bubbles. We will try to map the non-ionized neutral hydrogen. And for that, you have your H1 line in the radio, and you can study absorption or emission. Emission you can't study at those redshifts, but you can study absorption line systems to try and map the distribution of neutral hydrogen. So this is a completely complementary way to studying the ionizing sources. So JWST and other telescopes will be used to study the ionizing sources, while SK and other radio telescopes will be used to study the neutral hydrogen distribution. Okay. But again, as I said, we won't talk much about the reionization because I think that will get covered in your IGM course. Okay, so now we talk about, as I said, looked only at low redshift galaxies so far. Let's now look at high redshift galaxies. In 1995, when I was taking this course, or an earlier variant of this one, only a few galaxies with redshift greater than 1 were known. Most of them were radio galaxies, which were discovered by optical identification of radio sources. Very distant galaxies are very faint, and detecting galaxies at high Z is very difficult process. If you did a blind spectroscopic survey, which means you just find faint galaxies in your HST image or whatever, and you just go and get a spectrum of each one of them. This is problematic since galaxies with R less than 22 typically have redshifts less than 0.5. And spectra with R greater than 22 are only observable with 4-meter telescopes or greater than 4-meter telescopes, and with a large investment of observing time. So no time allocation committee will give you time if you say that I'm going to just blindly go and obtain spectra of one galaxy after another, hoping to find a high redshift galaxies. So this is also a problem of finding a needle in a haystack, because this process is slow, but is also very inefficient. So because even if you take galaxies as faint as 24.5, most of them will have redshift less than 2. So you will not be able to find a redshift 3 or redshift 4 galaxy, even if you do faint galaxy blind surveys. So the question is, how can we detect the small fraction of galaxies with high redshifts, right? You have to do that by having some kind of pre-selection. Don't try to get a spectrum of every faint galaxy. Identify faint galaxies that are likely to be at high redshift and only obtain a spectrum of those galaxies. That will give you a hit rate or an efficiency which is much higher than otherwise. Okay, what strategy you should adopt is illustrated by the spectrum of this very high redshift quasar, This is a spectrum obtained with the Keck telescope. This quasar is at a redshift of 6.43. So you can see the redshifted Lyman alpha line, you can see the other Lyman lines, and you can see the Lyman limit. Okay. So now, is there any way in which you can think of that you'd be able to find this kind of object without obtaining the spectrum? With just broadband imaging, which I told you is very cheap. Spectrum is very expensive. Radar bands. Okay, you mean these ones? Correct. Yes, yes. So that is correct. So which band will have high luminosity for this quasar? Red meaning really red. I mean almost into the near infrared. Okay, beyond 9,000. And what do you expect to find below the Lyman limit? What will be the flux below the Lyman limit? Very less, nearly zero, because the high energy photons are getting absorbed beyond the Lyman. Whatever photon comes with a wavelength less than the Lyman limit, slightly less than the Lyman limit, is whenever it encounters a hydrogen in its parent quasar, in the IGM, in our galaxy, anywhere, it will simply ionize that hydrogen atom and get absorbed. Okay, so if you look for galaxy fluxes such that at below, in a band below the Lyman limit, it will you will have no flux, virtually no detection of the quasar at all. But in a filter which goes above 9,000 angstroms, you will have a very strong detection. Then you have gotten narrowed down a high redshift quasar candidate or a high redshift galaxy candidate. Doesn't matter. Galaxies also, they don't have so many emission lines, but they have the same broad continuum spectrum. They'll have, if it's a star forming galaxy, you'll have Lyman alpha emission. You'll have the Lyman alpha forest on one side, and you'll have the okay. Right. So today, hundreds of galaxies and quasars with redshift greater than 6 have been discovered using this technique. So how do you find high redshift galaxies? To summarize, first of all, don't do blind spectroscopy of faint galaxies. That doesn't work. One thing you could do is via narrow band imaging, which means suppose you have a star forming galaxy, right? And there is a H alpha line that you will always be present there. If you can measure narrow band fluxes of this galaxy using a tunable H alpha filter, then once you move it to the redshifted H alpha line, suddenly you will get a strong flux. Okay, and otherwise you won't get fluxes. So there have been these kind of studies where what you do is you take a large field of view and you move your tunable H alpha filter, you change its pass waveband to different wavelengths, and different galaxies will get detected each time, right? And yes, correct. So I have a tunable filter which I'm moving, I'm changing the wavelength of that filter, pass band of that filter. So suppose I want to look for H alpha, let's say, which is at 6,000 angstroms. Suppose I tune it to, let us say, at redshift, probably Lyman alpha is better because that will take you into the optical. So the Lyman alpha is at 1216 angstroms, right? So suppose there's a galaxy at redshift 2. Then if I tune my filter to 3600 angstroms, I'll pick up the redshift 2 galaxy. If I want to pick up redshift 3 galaxies, I tune my filter to 4800 angstroms. If I want, if I go to 6000 angstroms, I'm going to pick up redshift 4 galaxies. So I can keep on changing that, and I can get galaxies at whatever redshift I want. So there have been large projects, particularly with the Subaru telescope, that have used narrowband emission, Lyman alpha emission lines to study, to identify high redshift galaxies at different redshifts. But what we saw in the previous slide is what is called as the dropout galaxies, dropout technique to find what are called Lyman break galaxies. Since hydrogen is so abundant and its ionization cross-section is so large, one can expect that photons with below the Lyman limit are heavily absorbed by neutral hydrogen in its ground state. Therefore, photons with this have a low probability of escaping from a galaxy or traveling through the IGM without getting absorbed. So those are the objects that we can use. So again here, one can use, just like with the dropout technique, one uses a tunable filter to find the galaxies at different redshifts. With the dropout technique, one uses different sets of filters to find galaxies at different redshifts. So one set of filters may give you galaxies at redshift 3, another may give you at redshift 4 or 4.5, and so on. I have a meeting starting. Yeah. So this method was first extensively applied in 1996 by Chuck Steidl and collaborators at Caltech. But now it has been used by many, many people to find literally thousands of galaxies at redshifts greater than 3. Okay, so we will stop here. If there are any questions, I'll take them. Otherwise, we meet tomorrow. Go ahead. Yes. Yes. You will find, of course, you don't know beyond a point, you don't know how many objects there are. Beyond a point, you don't know how many galaxies. Number density is also not constant, right? Galaxies are forming, new galaxies are forming at different points. Galaxies are merging, so that may reduce your number density. So that is not constant, but you're right in this general sense that once you sample a larger volume, you will find galaxies. There are lots of high redshift galaxies. Yes. If they're fainter, then what happens? We'll tend to find only bright objects. And if there will be a Malmquist bias. So that is why this technique avoids to a large extent the Malmquist bias. This chaos is caused by the Malmquist bias, wherein if you go to faint galaxies, faint objects can be nearby inherently faint objects or relatively luminous but very distant objects. And that is why your efficiency goes down if you do blind spectroscopy.